We have integrated computers into many aspects of our lives. However, a computer's most important property is also its most limiting factor. A computer will only do exactly what we tell it. In emerging applications, like driverless cars, the sheer number of variables to consider makes it infeasible for software engineers to write a rigid set of instructions for computers to follow. Machine learning is a subset of artificial intelligence designed for these applications. It refers specifically to creating computer algorithms which can improve over time. In this project, I'll focus on a specific form of machine learning, the neural network, and how I can apply it to drive a virtual vehicle. According to documentarian Seth Bling,
this structure of colored lines and blinking boxes is called a neural network. It's a simple mathematical model for how a brain works, but it can produce some very complicated behavior.
Just like a brain, neural networks have many interconnected neurons. However, instead of being on or off, these digital neurons can be any value in between, called the activation. These neurons are organized into layers, which can reflect different steps in processing data. There are input and output layers for interacting with data, and hidden processing layers in between. In neural networks and deep learning, Nielsen shows that each neuron calculates its activation using this formula. It considers the previous layer's activations, each with an adjustable weight. The weighting decides the influence a neuron has on the final activation. The neuron also has an adjustable bias, which offsets its entire output by a fixed amount. This sum can get quite large when expanded, so Nielsen explains how we can simplify it to a dot product of a weights and activations vector. This is computationally important as GPUs are heavily optimized for matrix operations and can enable running performant networks. We can further simplify the network by considering the connections between entire layers as matrices, meaning that we can describe the network through several matrix multiplications. In learning activation functions to improve deep neural networks, Agostinelli et al. Explain how as a network processes more layers, its activation values can grow exponentially. We can use activation functions, such as sigmoid, to regulate these to more manageable levels. Sigmoid confines activations to a range from 0 to 1 using a logistic curve. It was historically widespread but has since been superseded by ReLU. ReLU, or rectified linear unit, promises to regulate activations without sigmoid's detail lost from crushing inputs to such a confined interval. It ignores negative inputs while leaving positive inputs intact. In large networks, ReLU can introduce the dying ReLU problem, where the function's linear nature can get neurons stuck with zero activation. There are some variations of ReLU that address this problem, such as leaky ReLU, but haven't yet become mainstream. Neural networks improve through a process called training. But what is training? Essentially, it's a lot of trial and error. We run the network on example data that resembles what we would eventually like it to process. Let's say we'd like this network to train to recognize handwritten numbers from these low-resolution images. We'd like it to use these 10 output neurons to indicate which number it thinks it sees. As the network first processes the data, its responses are essentially worthless. We initially filled its weight and bias parameters with random numbers, so it's acting randomly. While it is training, we can tweak these parameters to try and find an ideal configuration so that it will reliably guess correctly. Doing this by hand would be impossible, but luckily we can find this configuration mathematically. The more time we can spend fine-tuning the network's parameters, the better it will perform, but as I learned from experimentation, this can take a long time. In a documentary series, Sanderson discusses the training process in detail, specifically bringing up cost. Cost is a mathematical function which measures the quality of a network's output and should be as low as possible. We define the cost function so that we reward a high-quality output, in this case, guessing correctly. As we run the network on thousands of inputs during training, we calculate each output's cost by comparing the result to a correct answer. Sanderson shows how we can use the cost to work backwards through the network and find which specific parameters to change through backpropagation. Backpropagation performs gradient descent to minimize the cost function. By minimizing the cost, we can maximize the network's performance. Nielsen elaborates on how gradient descent works in minimizing the cost. Using partial derivatives, we can define a gradient vector, nabla c, which describes the steepness of the cost function at any position. It can be difficult to understand gradient descent without a graphical example, so let's have a look at a simple case, a network with two parameters, v1 and v2. A plot of the cost function creates a 3D surface. We first choose a starting point on the surface, symbolizing the initially random parameters we filled our network with. Next, we find the gradient vector, which gives us the direction we should move to increase the cost most quickly. Since we want the opposite of this, let's define a new vector, delta v, as the negative of the gradient, indicating that we will move in the opposite direction. Each step, we move by adjusting v1 and v2 according to delta v, until we eventually reach a minimum. Notice how this works no matter which starting point we choose. It can be helpful to think of it like rolling a ball down a hill. Sometimes, if delta v is too large, we can end up overshooting the minimum. We can fix this by adding a small parameter eta called the learning rate. If we increase eta, the network will learn faster, but also has a higher risk of overshooting the minimum cost. In an interview, Dibiedma emphasized that a neural network's configuration can adversely affect its output. The number of neurons and layers, activation function, training time, and dataset size all influence how well a network will perform at a given task, so it's important that I choose this configuration correctly. Let's revisit the network that I discussed in the previous section, which I developed during my research. It is processing the MNIST dataset, a digitized collection of thousands of handwritten numbers. Each image is a tiny 28 by 28 pixels grayscale, making some of them challenging for even humans to read. MNIST has become the de facto standard in machine learning benchmarks. LeCun et al. State that the most capable techniques today can reach 99.5% classification accuracy. While configuring this network, I knew that the input layer needed 784 neurons, one for each pixel in the image. Similarly, as there are 10 possible digits from 0 to 9, the output layer has 10 neurons. I wanted the network to output a high signal on just one neuron, depending on which digit it classifies. The number of hidden layers was a mostly arbitrary choice. I ran several training sessions with different numbers of hidden layers, but found for this application, it just increased the training time. Nielsen recommended using sigmoid for networks that analyze MNIST, as it better preserves the relationship between changes in weight and changes in output for input values close to 0, like the brightness values in these images. Let's see the network in action. I developed it using the Unity game engine, so I can interact with it in real time. I included functionality to use a drawing tablet to input numbers, which the network can analyze as I draw. I achieved a reasonable accuracy with just several hours of training. Although it has its weaknesses, I was very happy with this first experiment in implementing a network. Once I had built my understanding of neural networks, I tackled my research question directly, creating a network to drive a virtual vehicle around a track. A weakness the MNIST network experienced was very unoptimized code, which increased the training time. So in controlling a virtual vehicle, I instead used Unity ML Agents, a free package which adapts Unity for training neural networks externally. This way, I could still create a fast network while taking advantage of Unity. I used the Unity Standard Assets Vehicle, a fully simulated vehicle bundled with Unity. In an interview, Cooper proposed that the Standard Assets Vehicle's physics simulation would add an extra layer of challenge to controlling it. This could show a network's superiority to a handwritten algorithm. I chose the track Donut Plains 2 from Super Mario Kart, since it has a large variety of track elements, including S-bends, U-bends, and long straights. Dibiedma's findings supported this decision. Incorporating many diverse track elements allows the network to generalize well to other similar tracks. After importing this track into the Unity engine, I followed Cooper's advice, who suggested that I place checkpoints around the track to create an intermediary goal for the network as it drives. In an interview, Harrison described PowerSlide's neural network input implementation. Each vehicle measures the angle and distance to checkpoints spaced around the track. In this project, I will instead use many raycasts fanning out from the front of the vehicle. In Unity, a raycast is an invisible line shot from a point, which can return useful information such as the distance. We can use these to create a primitive eye that sees distances to nearby obstacles. This is similar to how early 3D raycasting games such as Wolfenstein 3D drew environments. I use 16 raycasts, so the input layer of the network has 16 neurons. The standard assets car accepts two inputs, one for steering and another for throttle, so the output layer of the network is 2 neurons wide and is connected directly into the car controller. Unity ML Agents has a reward system, where network behavior is incentivized or punished through a reward score. I configured the network to receive a large reward every time it passes a new checkpoint. This encourages the network to keep driving forwards. I also persistently apply a small penalty for existing, encouraging the network to drive faster and collect more checkpoints to minimize the total reward loss. With these base systems in place, I had the foundation I needed to start training the network. But first, I made some further adjustments. The first modification I made was adding borders that better follow the shape of the road, since otherwise there isn't a way for raycasting to detect the edge of the track. Here is how the network drove during initial training runs. Its goal is to drive through each checkpoint and complete as many laps as possible within 5 minutes. Although right now it prefers to get stuck in corners. To solve this, when a vehicle is stationary for more than 5 seconds, I reset its position and give a large penalty. I noticed that the network specifically had difficulty traversing this region of the track. This was due to the network not yet learning how to turn right. I enabled the vehicles to start at any checkpoint around the track to try and better expose the network to more course elements. I also added more checkpoints around challenging corners to better reflect the difficulty of these regions and to proportionately reward the network for traversing them. After these tweaks, the network could finally make laps around the track. I was surprised at how quickly it learned compared to the MNIST network. After 5 minutes of training, the network made its first lap. After 15 minutes, it could drive with minimal crashes. And after an hour of training, it traverses the track at high speed with no difficulty. Here is how it looks with the barriers hidden. I wanted to test the adaptability of the network after I saw it accidentally run through the track backwards. I imported some more tracks from Super Mario Kart, and I was excited to see the network generalize so well to navigating them. It even tolerated me placing small obstacles in the track ahead of it. With this, I have successfully resolved my research question, having created a working network to drive a virtual car.